Okay, good afternoon, guys. Today we will talk. Today we will talk about the last linear model for classification, which is called support vector machine. And then we have the code problem solving for today. We will just play with scikit-learn. So let's start from motivation. So assume that we have some points of one class and another class. And we want to separate them. So we can draw a line, for example, like this. We can draw a line like that. We can draw a line like this. Which line do you think is better? They all separate our points, so it's hard actually to say which line is better. But what do you think? Just which line will you choose? Red, which is orange, red, blue, or green?
Right. Maybe green because it has a positive slope, so where the actual difference.
Well, as I said, there is no actually answer, one answer. So your hypothesis that is the green because it has a higher slope, but
No, just because the orange separation also has a positive slope, so.
positive.
Yeah.
Why orange?
Yeah.
Why red or orange?
Because it seems to have like the least, I guess, difference to each of the points, maybe. Like,
Yeah, so I also would choose this red or orange line because the green line goes very close to one class. The this line red it has kind of equal distance between both classes. So this is the idea of the support vector machine. Yes, feel free to take it. Paper, because if we shift, let's see, can I shift? Yeah, for example, if we shift this line at some point, we will hit one of the data points, and we can't move this line further because then we will get the incorrect classification. And the same if we move this line down, at some point we also will hit a point, but if you look at the example below, we have blue and orange lines. And for orange line, the width of the strip where we can actually move until we hit our point, data set point, is wider. And this is the points that we hit are called support points or support vectors. That's why this algorithm is called support vector machine, because we kind of try to maximize the distance from our line to the nearest support point. So this algorithm would choose orange line because it has wider wider strip without points inside this strip.
So let's formulate this mathematically. The distance from a point to the decision line is given by this formula. So without y, this is just the distance. You remember we proved the dot product over the weights, and now I'm using notation W for intercept and W for all other coefficients. Like earlier, we used notation W without 0. So this is the formula for distance. And we want to maximize the distance. So in this line below, we kind of calculate the distance for every point xi. And we choose the smallest distance. So, for example, we have points here. We can calculate the distance to one point, to another point, to the other point, for other points. So we calculate all possible distances and choose the smallest one. So the smallest one we denote by m. So this is just mathematical formulation of this text description. The distance to the nearest point. And as we stated our algorithm, we want to maximize this distance. So we want to maximize this smallest distance. So this is the formulation, but to make this algorithm more simple, we also will add additional constraint that for a line that goes through our closest point, the equation of line, so for this line, for decision boundary, the equation is W transpose. I skipped the bias term, it should be W0 plus W transpose X equals 0. For this line, the equation is W transpose X equals some number alpha. And I hope you agree that we can divide by alpha, and then we will get equation W0 plus W equals 1. So we will assume that for the line that goes through the closest point, we have equation W equal X equal 1, and it's easy. You can just divide everything by alpha, and you will get equation Wx equals 1. So just renormalize the coefficients. We don't know W, we don't know alpha, but that's why this function depends on W. And we will maximize this distance. Yeah. So, yeah. But when we assume that the distance to the nearest point, sorry, not the not the distance, but the dot product is 1. So if we assume that the distance, well, this is the dot product for the support point to the nearest point is 1, then this expression will be 1. So we kind of rid of this minimum with this normalization. So this will be 1. And our problem will be simplified instead of minimum over W, we will have 1 over W to maximum. But at the same, we will have this additional constraint. And we can reformulate this as follows. As this
Problem, we want to maximize M, which is now just 1 over W base. But with additional constraint, the smallest value for margin can be 1. Because the distance to the nearest point, we assume it's is 1. This value for points like further points, this distance will be only greater than 1. Okay, so
this is the mathematical formulation, and because M is 1 over W, then it's the same as minimize W. So if we want to maximize fraction, we can minimize denominator. So that's why we go from this problem to this problem.
Instead of maximize 1 over W, we minimize W. Also, we add square to make this quadratic optimization problem a factor, just because when we take derivative, two will cancel out.
Great, and that's it. The quadratic optimization problem
with linear constraints is a well-studied optimization problem. It's called convex optimization because quadratic functions and linear functions are convex functions.
And convex optimization problems are well studied. Now let's talk about non-separable case. Actually, we will talk about how to solve constraint optimization later today. So non-separable case, it's a little bit more tricky. So we have separator, but we may have points on a line with dot product equals 1. Here dot product equals 0. And here are some points with dot product equals -1. But the margin will be 1 because for negative class, the label is -1 and the margin is label times dot product, it will be 1. But assume that we have some points here. And at the same time, we have a point of the negative class here.
In this case, you can draw a line such that all points will be classified correctly. You can try, but you won't succeed in this. So in this case, we will allow some points to be classified incorrectly classified. So
let's denote by xc the distance from our support line. So this will be xc. For this point, this will be xc for this point, very small. So we call this slack variables. So for example, X1, X2. In other words, on these lines, which we call support of our algorithm, margin equals 1. But if we subtract a positive number, subtract c, it means that we can kind of shift this line by this c value. So in other words, let's look at some examples. For example, what if x is 0? If x is 0, it means that point actually lies either on this line or behind this line, because margin will be greater than 1 or equal. If x is 1, where we will have our point if x is 1? If x is 1, our point can lie on the decision boundary. So if x is 1, then we will have here 1 minus 1, 0. So if x is a large number, for example, 100, where will be our point if x is very large number, for example, 100? Our point will be somewhere here from this line. So we introduce these positive numbers c, and they represent the kind of error, the distance from the lines with dot product 1. So it sounds good, but there is a problem. There is a problem that you can choose another decision boundary, like here. And all the points will be classified as positive class because you can use very large c, and every time actually you will get correct inequality. The dot product is greater than 1 minus c, but it's not a good classification. So to avoid this large c values, we will force this c to be small. So that's why we introduce this term. So this term was our original objective function, but we also add this additional term to force our c to be small. And this is actually the mathematical formulation of the problem for non-separable cases. And now we will solve this problem with so-called Karush-Kuhn-Tucker theorem. So let's look at this theorem. Karush-Kuhn-Tucker theorem is a theorem about optimization problem with constraints and with linear constraints. And there are two types of constraints: inequalities and equalities. So I will just formulate here, or prove it. You can reduce constraint optimization problem to unconstrained optimization. And for unconstrained optimization problem, you can apply gradient descent, for example. So to reduce constrained optimization problem to unconstrained, we use the so-called dual formulation.
and introduce Lagrange multipliers, Lagrange function that by L. It's not loss, it's Lagrange function. And instead of minimizing original function, we will maximize the Lagrange. So the Lagrange function looks as follows: our objective, then our inequality constraints multiplied by some numbers lambda, and our equality constraints multiplied by some numbers mu. And then we should minimize this function with respect to x. So when you minimize with respect to x, you will get function only of lambda and mu, because x will be optimal. And after that, you will maximize this function. It's called saddle point, but minimize, maximize. You will just maximize this function, but in new variables. Let's look at the example to make it more clear. Let's assume that f is just parabola. For example, f is x squared, and constraints are x greater or equal to. So just example. If I draw this, it looks like this parabola, and x greater or equal to. So what is the solution for this problem? What is the smallest value of our function with constraint x greater than? Where will be this point? This point will be here on at x equals 2. So this will be the smallest value. The smallest value that our function can take with these constraints, because x can be smaller. But we could solve this by observation. How to solve this if the number of variables is 100, or you can solve this by observation. And then this Hirsch Kuhn and Tucker theorem, these are 3 people, is helpful. So let's write a Lagrangian function. So I will rewrite this constraint as 2 minus x smaller than 0, just to get the same inequality sign. And then the Lagrange function will be our function x squared plus lambda times constraint. So this function depends on lambda and x. First, we will minimize with respect to x. So we can take a derivative with respect to x and equate to 0. So it will be 2x minus lambda. And we find the optimal 0x lambda over 2. Then we substitute this x into our Lagrange function. So it will be lambda squared over 4 plus 2 lambda
minus lambda times lambda over 2, it will be lambda squared over 2. And finally, we maximize this function with respect to lambda. So we take again derivative. So you can see I just take derivatives. I don't care about constraints anymore. It will be lambda over 2 plus 2 minus lambda plus 2 minus lambda. And when we solve it, we will get the optimal lambda so we will have lambda over 2 equals 2. So lambda is 4. Now, if you substitute lambda equals 4 to x, what will be the value of the optimal point? It will be 2. So it was easy to solve by observation in one-dimensional case and with one constraint, but with multiple constraints, it's easier to use this dual formulation. Okay, so now we will apply this dual formulation to our support vector machine. So this is our function f. This is our equality constraint on the boundary margin equals 1 minus c. And our inequality constraints c greater than 0. C greater than 0, this was inequality constraints. And now we take the derivatives. Derivative with respect to w results in lambda y. Derivative with respect to w results in w from the first term and lambda from the second term. So this is the derivative with respect to w. And derivative with respect to xi gives us c minus lambda minus mu. And now we just should solve this equalities. And we can consider three cases. If lambda is 0, then from this equation it follows that mu equals c. C is qualified parameter. Mu equals, so mu is not 0. If mu is not 0, then xi should be 0. If xi is 0, it means that our point lies outside of this strip. So this is the first case. If xi is 0, then x doesn't affect our decision boundary. It means that actually we don't need to go for all the points in the dataset. We just need only these support vectors, support points for classification. You can just remove all other points, throw away, and save computation. So the second case, if lambda is between 0 and c. If lambda is between 0 and c, so lambda is not 0, then this term should be 0. But on the other hand, mu is c minus lambda, so it's again non-zero. And it means that xi is 0. If xi is 0, it means that margin equals 1. If margin equals 1, it means that our point actually is a support vector. And the third case, if lambda equals c, then mu is 0, and we don't mu is 0, and if mu is 0,
then Xi might be not zero. If Xi is not zero, it means that point lies actually on the other side of our support line. So it's kind of three cases. If lambda is zero, then our point lies outside this strip. If lambda is in between, then it lies exactly on this line. So lambda in between 0 and C. And the third case, when lambda is equal to C, we allow our points to lie kind of behind this line. And for large lambdas, even maybe here. So, but we still need to solve our equation. So we just consider three cases, but still we need to define lambdas. And then, bless you. And then, as in our example with parabola, we define lambda, and then we use lambda. If you look at the equation on the top, it means that W equals the sum of lambdas times Y. So if we define lambda, we will define W. So we kind of solve our problem in variables lambda and U, but then we go back and we solve for W. Because our goal is to find actually the weights. Yeah, so how to find these? So we will substitute W equals this sum. To our objective function, and in our objective function, we had W squared. So instead of W squared, we will multiply sum of lambda y's times sum of lambda y's. So we will get a quadratic function with respect to lambda. And now we have this problem. X, our features are given, y's, our targets are given. The C is the height parameter is given. And we have a quadratic function with an interesting, it's still constraint optimization, but now it's a much simpler constraint. Now our lambda lies inside the cube of the side C. And this problem is easier to solve. You can just go for every face of your cube, and then you will reduce your dimensionality at least. Okay, so this is the exact solution of this problem. In practice, we a little bit cheat. So in practice, we introduce the notion of so-called hinge loss. So hinge loss is a function. So if this is a margin, then 1 minus margin goes like this. And for negative values, we just clip this by 0. So how it's related to our loss function? So as you remember, we had equation, this margin is greater than 1 minus Xi. So we can rewrite this inequality as Xi greater than 1 minus margin. So, as you remember, in our loss function, we had the sum of these slack variables Xi. We the goal was to minimize C. But if our C can be smaller than this value, we can just change the C by this value, by 1 minus y. Also, we know that C can be 0. That's why we click by 0. And now we will minimize this function without any constraints. So you can just apply gradient descent, but this will be your loss function. And in scikit-learn, you can run gradient descent with this loss function, and you will solve actually support vector machine problem. So instead of using the exact solution with constraints, you can use this trick. So let's talk about the C variable. So if you think about the product between two numbers, if one number is large, then the other number can be small, and vice versa. So if the first number is small, the second can be large. So it's exactly the same idea here. If our, let's look at the examples. If our C is small, it means that the slack variable C can be large. What does it mean? It means, like here, let's say we had a support line here, but because C can be large, we can allow the misclassification. So for small values of this constant, our algorithm can allow misclassifications. If this small is large, like 5, it means that the error C should be small. So if our decision boundary is here, the error can be large. So we don't have misclassifications. Of course, some points can lie inside this strip, but but not far away, like in the previous case. Okay, that's it about algorithm. Now let's go to the code and solve the notebook. So yes, support vector machine was proposed in late 90s. So it's not pretty recent algorithm, and it was the most popular before gradient boosting that we will cover after the break, right after the break, and neural networks. Okay. So before we just use support vector machine from the box, out of the box from scikit-learn, I want you to look at our 3 models. Logistic regression, so we have loss function like a log of 1 plus e power negative margin, and for all the points we took the average. Linear regression, when we use hard classification. Hard classification means that if the sign is positive, we return 1. If the sign is negative, we return negative 1. And and by the way, if the sign is different, so it means that we make an error. So if the sign is the same, I think again, not equal is missing.
So okay, not equal. So
Because we want to add one only for misclassification. So if our point is misclassified, then we will get this condition will be true, and the Calibration brackets will result in one. We will add one to our loss.
so how it looks like, and finally hinge loss. If we plot these three loss functions, so these are loss functions only for one data point. Then the blue line corresponds to the hard classification. If we don't make an error, the loss is zero. If we make an error, then the loss is one. The orange line corresponds to log of 1 plus e to the logistic regression. And you can notice here that it returns the probability. Even if our margin is very, very large, it still will hesitate. It will say, well, it's a positive class, but with probability 0.999. And the green line stands for support vector machine for hinge loss. It again will penalize incorrect classification when our margin is negative, the loss will be large. But after some point, it will provide hard classification. So it's just positive class and no doubt. The only difference is in this region when the dot product is zero. So this is kind of the most uncertainty in every model, except the hard classification. And as you can imagine, when we use different loss functions, we will get different weights. So the slope of our line will be different for these algorithms, but we will plot it later. For now, let's just classify. This data set is called noisy moons, and this is not separable case. We fit just logistic regression, and logistic regression has parameters intercept and coefs. So to plot the decision boundary y, I can solve this equation for y. So it will be negative w0 plus w1x over w2. So in my code below, actually, I just implement this formula.
So this is intercept is w0 plus w1 times x1 and divide by w2.
So this is how I plot this blue line. First, before we go to our problem, so I want to mention for your homework how to change the threshold. So by default in logistic regression, it's 0.5. If we want to change to 0.4, and this is confusion matrix, true label is 0, the prediction is 1, so it's false positive. We have 7 false positive and 9 false negative. So we have 41 true positives, and if we divide by positive predictions, we will get precision, and if we divide by the total number of positives, we will get recall. But you can use built-in functions. This is just a reminder. So then we can we can return probabilities. As you remember, predict probe returns 2 columns. 1 column for one class, 1 for another class. But the question is, which column corresponds to which class? To answer this question, you can use this attribute classes, and it will actually return the labels. And it turns out that for class 1, in this case, we have the second column, not the first one. So that's why for positive class probability, I'm using index 1, not index 0, but not index 1. So to apply threshold, we can use this positive class probability greater than 0.4. And then we will get predictions for new threshold, and the previous false positive number was 7, because we moved our threshold down. Now we have more points predicted as positive. So that's why the number of false positive also increased. But also the number of true positive increased. Okay, so in your homework, you can just write a for loop with threshold between 0 and 1. And I ask you to choose a threshold such that you get specific recall. So you just run different thresholds, and you will choose a threshold when you will get the required recall value. Okay, now let's go to the problems. Oh, one more. Okay, this is just one more example. I plotted precision and recall curves and F1 score, just to show that the maximum of F1 score will be in the intersection of precision and recall. Just as you remember, we use F1 score to maximize both and precision and recall. So just illustration that that it's true that it maximizes both and precision and recall. Okay, ROC curve. This is PR curve. As you remember, it's monotonous, and ROC curve, which is monotonous. So in ROC curve, you shouldn't use the predictions. So you can't use here threshold like greater 0.4, because then you will get incorrect plot. Please use the outputs of your model, because under the hood it just applies different thresholds. If you have in your predictions just 2 values, 1 and 0, or 1 and -1, there will be only one threshold. Okay. The last comment before problems: how to get nonlinear decision boundaries. The answer is instead of features, use non-linear functions of these features. For example, instead of x, use x squared or sine of x. And here is example. I'm applying, I extend my features with x squared and the product of two components x1, x2. And as the result, the decision boundary looks like this. Quadratic function. If you want to get the cubic decision boundary, you should apply features with the third power. So in this example, as you remember, polynomial features create power 0, power 1, power 2, and the product of x1, x2, and all power and power 3, like x1 squared times x2, and so on. So if we introduce these polynomial features, the decision boundary looks like this. So we spend a lot of time talking about linear functions, linear decision boundaries, but you can generalize this for non-linear decision boundaries, just use instead of x function. Finally, support vector machine, our first problem. Just apply the support vector classifier from the box. Support vector classifier just with default parameters dot fit and plot the decision boundary. Plot decision regions. And you can see that right from the box, this support vector machine works pretty good. By default, it uses non-linear features. By default, it uses so-called Gaussian kernel. The formula looks as follows. So by default, the features are exponents to this negative power of x squared. And A is, so for example, we have 10 points in our data set. So A is one of these points. So we create n features where A is one of the n points. By default. But problem two, let's use kernel linear to get the linear decision boundary. So just copy paste. And use this parameter kernel linear. Then it will plot a linear decision boundary. But I also ask you to plot the support vectors. So to plot something like this. So I will copy paste the code for the line from above. But instead of regression, I will use SVC. So it will plot this blue line. But now we also need to define the support vectors. And these are vectors with equation margin or absolute value of dot product equals 1. So you can just use this code is close to 1. So and p apps W0 is the intercept. W1 is the first coefficient. Times first feature plus the second coefficient times the second feature. So is close to 1. One is missing. We'll return this table where true will stand for actually the support vectors, the points with marking equals to 1. So now I will just take these indices and this is the list of support vectors. So I will plot it. Oh, sorry. Let's denote this by support vectors. And I will plot scatter plot these support vectors. Okay, so now we have these. Yep. Yes. So but we want to plot the lines actually, like here. So to plot these lines, we should plot the equation. We should plot the equation where dot product equals 1 or -1. So it means that instead of W0, we will use W0 plus 1 or -1. Does it make sense? That if here is 1, we just put this one to the left and it will be W0 minus 1. So I will just copy this line and add 1 to my intercept and -1. And voila, we have this lines that go through the support vectors. We are almost done. I ask you to repeat this with additional parameter C. Just add C equals 0.2 and C equals 5. Just copy paste 2 times this code to see how the width of this separating strip will be changed depending on C values. Meanwhile, I will plot the decision boundaries for logistic regression and for linear regression on the same plot to show the difference. So, for example, for logistic regression, the decision boundary is close, but not the same. And I will plot for linear regression. You don't need to do this. It's just for illustration. But for linear regression, because labels are 0 and 1, the decision boundary will be 0.5. So I should subtract 0.5. So you can see that green line is support vector machine, blue line is logistic regression, and orange line is the linear regression. So they result in a little bit different decision boundaries. So did you notice that for small c, this strip is wider, and for small it's more narrow? Okay. Okay. Finally, I want to talk about the model calibration. So all the models have parameter predict proba. So for example, our support vector machine also has this parameter, but if I just call it like predict proba, I will get an error because to call it, you should use parameter probability equals true. By default, it's false to make it working faster. So if you use parameter true, then you can use predict proba to plot ROC curve. Because to plot ROC curve, you need actually the model outputs, not the hard predictions. But only one model, which is logistic regression, returns true probabilities. Other models, they return some numbers between 0 and 1. For example, in linear regression, you can just convert the distance into range 0, 1, but it doesn't mean that it's a probability of the class. It's just some number. And this is called model calibration. And actually, it's the last line of the code. So you can see that this dashed line represents kind of true probability distribution of data, and logistic regression aligns with this line. But support vector machine, not very well. So there is a method which is called calibration inside here that will fix the output probabilities from predict proba, which are not real probas, and will make these probabilities, these outputs from the model all probabilities. So why do you think logistic regression predicts probabilities and other models don't predict probabilities, true probabilities? Do you remember how we actually trained the logistic regression? We maximized likelihood. And what is the likelihood? It's a joint probabilities. So that's why the model returns probability. Okay, so we are almost done. We have 4 minutes left. I want to tell you the story about this support vector machine. So the authors of this model were 2 scientists from Soviet Union, because in late 90s it still existed. Vapnik and Chervonenkis. Vapnik immigrated to the United States and now is professor emeritus at some Ivy League university, I don't remember which one. And also there was even theorem that neural networks won't work well. So it was late 90s, and now we all work with neural networks. So, but there was theorem that they won't work well. I will explain later why. It's not only because of computational powers. And support vector machine is the best model. So there is also notion VC dimension, Vapnik-Chervonenkis dimension. So it was very popular, but nowadays, I don't know who is using this model. The most popular model now is gradient boosting that we will code after the break, and then we will start neural networks. But Chervonenkis remained in Soviet Union and then Russia, and worked in Yandex school. Yandex is kind of Google, but in Russia it provides email services. It provides GPUs like Colab. I believe it's just copied Colab. And also it provides news in Russian edition. So, okay, I will skip this. If you want, we can talk about Russian propaganda later. So, and Chervonenkis worked taught in this school statistical machine learning. Well, actually, they proved also one theorem, very deep theorem in statistics, because working with data is just the statistics. We learn something from data. And about 3 years ago, he went, it was a winter, he went for a walk in the park in the suburbs of Moscow and lost. He was old and froze to death. So this is the history of this support vector classifier, which says that if you are a very clever person, there is no guarantee that you won't have your phone discharged or lost in the park. Okay, that's it for today. And yeah, now you are ready for next homework.